Hey you guys, I hope your week 2 was a little bit smoother than last week. Again, this material will come, there's a lot of material in this class, so just make sure you're keeping on top of it and really taking responsibility for your learning. There's a couple things I want to address, so let's do it, okay? One of them was that you guys were asking for more practice on some of the comments, and so what I did was in our Canvas course page. If you navigate to our Canvas course page in the first module called Course Resources, and under the headline of Resources, I added this external link. It's called Extra Practice. And I said, look for the topic you like more practice and click on it for questions. So if you click on that, it will take you to this online text. And so I think it was with like ionic compounds. And you guys wanted more practice, so if you go here and click on ionic, there's all kinds of different questions. There's some more exercises, and if you scroll down, the answers are there too, for the odd ones, okay? So there's more practice for you, so please check that out if you guys are looking for more practice on with any topic. It doesn't have to just be ions. Some of you mentioned that you were, I thought you guys could see the correct answers for your in-lecture questions. I've now adjusted the settings in TopAt, so you should be able to see the answers for the in-lecture questions. And so, yeah, but for homework, it's usually not going to, sometimes it might have the answer, sometimes it might not, just because your weekly homework questions are a little bit more involved. And so it's not always a straightforward process to get the answer in there, okay? And so also, a lot of you guys were asking me about, in the weekly homework assignment, I asked you to draw something or fill in a diagram. If I ever ask you to do that in Top Hat, and it's usually gonna be in your weekly homework assignment, there's not a way to do it in Top Hat. So just right, I did it on my paper, and you're going to receive full credit because the weekly homework assignment is graded 100% on participation. You did have one in-lecture question that asks you to draw a Lewis structure. We're going to look at that in this video. And I put a little note there that don't worry, I know you can't really do this easily in Top Hat. So this one in-lecture question is graded 100% on participation. So you can write something like, I did it on my paper, okay? But again, I want you to remind you guys that your weekly homework, this is your chance to challenge yourself and really assess if you're learning the material, right? Figure out how much have you learned and what are you struggling with, okay? So if you have a question, if you are struggling, or even if you feel really confident and you just want to process it with someone, come to one of the 5 office hours you guys now have available to you, okay? You can go into Mesa Tutoring. You can go to the Lark Center and get tutoring. You can connect with a classmate. Hopefully, again, I haven't figured out how to use Slate that well, but maybe you guys are. That's on my to-do list. Or again, email me, okay? But really, again, remember, one of my things I always emphasize to my students is that this is your time to take responsibility for your learning, okay? If what's I'm putting out there on Top Hat's not working for you, you need to take responsibility and figure out what does work for you. How do you learn best? Okay, so there's lots of resources. Even if we are learning online, there's still lots of resources, okay? So it's up to you. Take that responsibility. All right, so some questions I saw on the discussion boards. I didn't get to go through all of them and answer all of them. And again, Dr. Sherritt, Dr. Farmer are helping me. We had a little glitch this week where, Dr. Sherritt, for some reason, he was trying to respond and it just wasn't posting. But I went through, and again, if you guys can like the questions you have, that's what I did. I said, where's the most liked? And I'm gonna address those questions now. Also, I know I went over with a student and it looks like you guys have to do something, like leave a comment because it says you have 5 out of 6 things done, or there's always like one thing missing if you haven't posted a discussion board. But again, don't worry, you're not gonna get docked if you don't post. But I do love it. I love the feedback because some of you guys are telling me like, this is really clear. I really get it. And some of this like, oh no, I need more practice. So that helps me to address your guys' concerns in these weekly videos. So again, someone asked in isotopes, again, like how do you write out an isotope like 12 carbon, you know, especially if you don't have the exponents available. So you can just write it like this, just a C-12, or if it was like C14, C-14, or if it was like phosphorus 32, it's the element and then the dash and then the mass number. How many protons and neutrons does it have? So like if it was phosphorus 32, just P-32, okay? So it's a simple way when you don't have exponents available. Okay. All right, a lot of you guys asked in the periodic table section, are we going to need to memorize the periodic table in the future? No, absolutely not. That's one thing I love about chemistry is that you always have the periodic table and it's an amazing tool. I don't expect you to memorize it. So you will be provided with a periodic table for each test, okay? But you should know how to use it. You should know that like metals are on the left side and non-metals are on the right side. And you should know that the last column, group 8 or 18, the last column to the right is the noble gases. And then the one next to it, the second to the last, it's group 7 or group 17 or 7A, depending on your periodic table, are known as the halogens. Those are really commonly referred to, the halogens and the noble gases. So be familiar with that. All right, a lot of you guys have questions about what's a valence electron, what's a core electron. And so here, looking at this picture here, let me move my face. But here, if we're looking at something like hydrogen, notice where hydrogen is on the periodic table. It's over here in the upper left-hand corner. We know that if you're in the first row, right, there's hydrogen and helium, you have one shell around you for electrons. And we also know that first shell can only hold 2 electrons, okay? So again, hydrogen just has 1 electron in that first shell. That's it, okay? Then we go over to helium. Helium's still in the first row. It only has 1 shell and it has 2 electrons. And remember that first shell can only hold 2 electrons and that's it, okay? So let's go a little bit more and then I'll talk more about it. Let's look at lithium. Lithium's the next one right here, right underneath hydrogen, okay? And so for lithium, it's in the second row, okay? So it has 2 shells to hold electrons. But remember, the first one can only hold 2, this gray circle, and then it has 1 more in that outer second shell. And then let's look at carbon over here, okay? Carbon, again, it's in the second row, okay? It's in the second row. So that means it's a second row, meaning period 2, meaning 2 shells to hold electrons. And that inner shell can only hold 2 electrons. And then the other, carbon has 6 electrons total. So 2 are in the inner shell and the other 4 are in the outer shell, okay? So in this diagram, the core electrons are the ones that are in the inside, and they are shown in these gray circles. So these blue dots on these gray circles are your core electrons, okay? The red circle represents the valence shell, which holds the valence electrons. It's the outermost shell. So for like hydrogen and helium in period 1, that first shell is its valence shell, and there are no core electrons for something like hydrogen and helium. Just that one shell is the valence shell, and it has 1 electron. But when we move to period 2, right, it has 2 shells. The innermost one holds the core electrons, and we know it can only be 2, okay? And then the outer, the second shell for the elements in period 2 in the second row, the second shell is the valence shell, okay? And then when we go down to like period 3, okay, the third row, well, now it has 3 shells that can hold electrons. And so the first 2 shells are holding all the core electrons. Remember, the first one can only hold 2, like we see around this sodium atom. It can only hold 2. But the next one can hold 8, okay? And then here's the third shell, okay, with that 11th proton for sodium, okay? And you can see the examples of silicon, chlorine, and argon, okay? And so when we're thinking about Lewis structures and the formation of ions, We really just need to understand how many electrons are in the valence shell, in the outermost shell. And the easiest way is to look at the number on top, okay? So again, that first column has 1 valence electron. The second column has 2 valence electrons. And we look here, the third column here has 3 valence electrons, and so forth. So like here, this is group 7 showing you fluorine. So fluorine has 9 protons, okay? So in a neutral atom of fluorine, there should be 9 protons in the nucleus, 9 electrons surrounding it. But 2 of those electrons are in the first shell. The other 7 are in the outer valence shell, and those are 7 valence electrons, okay? Now look at chlorine. Chlorine also has 7 valence electrons, but again, it's over here, number 17, telling us there's 17 protons in the nucleus. So if it is a neutral atom of chlorine, then that means there are 17 electrons surrounding it, okay? But look, let's see where they are. There's 2 in that first shell, another 8 in that second shell, and so 2 plus 8 is 10. That means there's 7 more. There's 7 in that valence outer shell, in that red circle, okay? And so again, it has 10 core electrons for chlorine and 7 valence electrons for chlorine. Again, the same as fluorine has also 7 valence electrons, but fluorine only has 2 core electrons, okay? So the core electrons are the electrons on those inner shells, and the valence electrons are on the outermost shell, okay? Notice when lithium forms an ion, right, to stabilize, it wants to lose this 1 electron. And when it loses that kind of the outer shell. And now this becomes, right, its most outer shell, okay? All right. Ooh, oops. Oh, a lot of you guys were asking about radiation. You were really concerned. And here, I think I put more information than I probably needed to on Top Hat, because when we're in class in person, you can tell like how quickly I go through it. And basically, there's kind of 3 points I want you to get. Is understand half-lives, okay? The amount of time it takes for 1/2 of a radioactive sample to decay. I'll go through each of these a little bit more detail, okay? I want you to know there's 3 types of radiation: alpha, beta, oops, mistake, gamma. Alpha is the biggest, it's the equivalent of a helium atom. Beta is in the middle with the equivalent of an electron. And gamma is like a ray, it's like excess energy, gamma ray. And the reason, you know, for pertinent to you guys is that often radiation is used in the medical field for diagnosis or treatment. And I want to make sure you guys know how to protect yourself, okay? And have knowledge of, you know, what's around you. So half-lives, okay? So when we have the decay, right, we're giving off this nuclear particle. And the half-life, if we start off with 200 nuclei, how long is it going to get to half that number? How long is it going to take to get to 100 nuclei that are radioactive, okay? And so on this particular graph, to get from 200 to half to 100, it took 3 years. So that's 1 half-life. And now we're here at 100. Well, to get to another half, to get from 100 to 50, it's going to be another 3 years for half of that radioactive mass to decay, okay? And then here, and going from 50 to get to down to 25 nuclei, it'd be another 3 years, another half-life, okay? So again, go practice those. If it's still confusing, come to office hours or Mesa or Lark, okay? Alpha decay, again, it's like a helium particle because it has 2 protons and 2 neutrons, okay? So that's a relatively big particle when it comes to radiation. Beta decay is like the equivalent of an electron, not much mass, and it's like removing a positive charge. Oh, it's like removing a neutron from the nucleus. It's kind of weird, okay? But again, just know it's in the middle, okay? Gamma is like excess energy, okay? So it's an unstable nuclide. It gives off some energy and then it becomes stable. Okay? And again, the main thing I want you to get is if you're in a medical field and you're working around radiation, you should know what type of emitter. Is it an alpha emitter? Is it emitting alpha particles, beta particles, or gamma rays? Because that's going to determine how far it can penetrate things around you. And you want to make sure you're protecting yourself. So alpha particles can be stopped by a piece of paper because they're so big. But beta particles are smaller, and so are gamma particles. They go right through a piece of paper. Okay, but beta can be stopped by 0.5 centimeter of lead. Okay, so those are like those lead aprons we wear when we go to the dentist and get our x-rays. Okay, gamma is much smaller, right? It's just like a wave of energy. So it can go through paper and even this 0.5 centimeter of lead. So you would need 10 centimeters of lead to stop a gamma emitter. Okay, and then just kind of where it's used in the medical field. So, and this is probably out of date. There's more of this going on now, but again, so here are some common isotopes, and they get used in diagnosis of different conditions in the body, and sometimes they're even used to help treat the body. Okay. All right, and then the last thing I want to talk to you guys about. Oops, yeah, that is the last thing. Is a lot of you were asking in the section on ions and Lewis structures. You guys had a question about the last in lecture question where it said, use a Lewis diagram to illustrate the formation of an ionic compound from a potassium atom and an iodine atom, okay? And again, I made this one 100% participation because there's not an easy way to enter this into Top Hat, but I wanna make sure we understand what I meant by this, okay? So again, if we represent a potassium atom, and let's just quickly go back. Sorry, I should have put a periodic table there. But if we look, potassium is in the first column. So we know it has one valence electron. And it's with iodine. So here's iodine. It's in the second to the last one, which is group 7A, also known as 17. So we know it has 7 valence electrons, okay? So we want to make sure we represent that. Here's our potassium with its 1 valence electron represented. And here's our iodine with its 7, 1, 2, 3, 4, 5, 6, 7 valence electrons, okay? And remember the octet rule, they want to reach an octet. If potassium lost this 1 electron, then it would have the next inner shell, and that would be full of 8 electrons. It'd be really happy. And if this iodine gained 1 electron, it would be really happy because now it has 7 and then it would have 8. So this 1 electron from potassium is going to be taken. It's going to give the electron to iodine, and iodine completely accepts it, and potassium completely loses it. When it loses that electron, potassium now takes on a positive charge, okay? It's a cation, and iodine takes on this negative charge. It's an anion, okay? And this together, their opposite charges are what attract it. It's a strong attraction and makes, oh, I'm sorry, I messed up there. It should be potassium iodide, not potassium chloride. And so that's what makes it ionic compound, okay? And so that's how we would have represented that problem with Lewis structures. All right, you guys, that's all I have to say. I hope you're enjoying your weekend. Please, again, make sure you utilize your resources. And as always, I hope you guys are healthy and I hope you are safe. Please check in with each other. Take care of yourselves physically, mentally, emotionally, spiritually. That's all important, okay? All right.